తప్పంటారు.
So we are giving this high-level language statement as input to this compiler. So this high-level language statement can be converted into assembly-level language. Here this operation is binary arithmetic operation, that's addition operation. This operation needs two operands. So these two operands need to be loaded in some register. So the assembly-level instruction is load the register, memory. That is the operand A, content of A is loaded in register R1. Okay, next we need one more operand, that is operand C, B, and one more load instruction to load the second operand C in another one register R2. Okay, so this addition operation needs two operands. So before performing this addition operation, both the operands needs to be loaded in registers. So this instruction will load the content of B in register R1 and content of C in register R2. After that, we can provide addition instruction add R1, R2, R1 to R. That is, the meaning of this instruction is content of register R1 and content of register R2 is added and the result is stored in register R1. Okay, so this is the output of this compiler. So the compiler will convert the high-level language program into assembly-level language, assembly-level program. So this is the output. Then this program needs to be converted into machine-level language by using another one system software. What is the name of the software? So assembler. So assembler is the system software which is used to convert the assembly level language to machine level language. So machine level language means it is in the form of some binary values. Okay. So for load instruction, first we have load to load instruction. So it may be, this is the machine level code for first load instruction, and this is the machine level code for second load instruction. Then finally we have add instruction. So this may be the machine level code for add instruction. Okay. So this classes, so this assembler itself having many subclasses to convert this assembly level code into machine level code. That topics are covered in a subject called system software. Okay, but that subject is not available in your autonomous syllabus. So no need to worry about that. Just you know that this assembler will accept mnemonic codes or assembly level language as input and convert it into sequence of machine level language as output. Machine level language means it cannot understand by the user, it can only be understood by the system or processor. Okay, so this is the output of assembler. Can you understand up to this? Any doubt? Okay, so after this conversion, what we have to do? What's the next step in program execution? The conversion itself is enough? No, right? So what is the next step? For execution, this converted machine code needs to be loaded into where? Memory, right? This machine level code needs to be loaded into memory for execution. How the machine level code is loaded into memory? Again, we need to use one more system software called loader. Okay, so loader is a system software which is going to load this machine level code into memory, that's main memory. Okay, this is the main memory. In the main memory, the program that is like code in the form of machine level, that is binary form. These codes can be loaded into main memory for execution by the loader. Loader is a system software which is going to load your machine level code into memory for execution. Okay, after loading the machine level code into memory, what is the next step? Execution process complete aayucha? No, right? What is the next step? Okay, where actually the execution is performed, in which part of the computer the execution is performed? Processor, right? CPU. Within the processor only the actual execution is performed. So, but here all the instructions all the machine codes are available in main memory now. So, these instructions needs to be brought to that processor. So, the CPU needs to fetch all these instructions from the main memory. CPU can fetch the instructions one by one. For execution, the CPU can fetch the instruction one by one from the main memory. Okay, then only the execution is performed within the CPU. So how the instruction is fetched? What are the different cycles in instruction execution? Already you have studied. Instruction fetch, instruction decode, there is one more phase, instruction decode also. Then execution. Instruction simply, when you say simply, there are only two phases, instruction fetch and instruction execution. And in some books, they have mentioned that there are three phases. Normally, there is instruction fetch, instruction decode, and instruction execution. Okay. So, instruction fetch. First, we are going to see what are the components inside the processor. Can you say what are the components inside the processor? The CPU. Within the CPU, what are the components available? Yes. ALU, arithmetic and logic unit. Control unit. Registers. Program counter. Memory address register. Memory buffer register. Instruction register. Okay. So these are the various components available within the CPU. First copy the diagram. Don't make noise, just copy the diagram. arithmetic and logical operation. Control unit is used to communicate with all the components within the processor, or it can give signals, that is, it can give read signal or write signal to the other components inside the processor. Then there is one program counter. Program counter is a register which contains the address of the next instruction to be fetched. Okay. Then the instruction register is having the instruction that are currently executing. Okay. Then in the fetch cycle, because we are to see in detail about the fetch cycle, instruction fetch cycle of program execution, instruction execution. In the fetch cycle, the address of the instruction to be fetched is available in program counter, right? Initially, the address of the instruction to be fetched from the main memory is available in program counter. So that address is given to the memory address register. Okay, this is the program counter is having the address of the instruction to be fetched from the main memory. So in the location instruction fetch pannumo and the location or the address வந்து எங்க இருக்கும் program counterல. So that program counter address is given to memory address register, because this memory address register is having the communication with the main memory through this address bus. Okay, this memory address register only having communication with the main memory through the address bus. Okay, so the address stored in program counter is given to the memory address register. So that address is searched in main memory. Suppose the address stored in memory address register is, for example, you take 1000. 1000 is the address stored in memory address register. So the particular address is searched in memory. Okay. In this particular address, there is some instruction is available in the form of binary values. Okay. So that machine code instruction is stored in memory buffer register through this data bus. So this is the data bus. Through the data bus, the instructions that are available in the location 1000 is given to the memory buffer register. So the memory buffer register is having the machine instruction in the form of binary values. Okay. So in the next, the content of memory buffer register is given to the instruction register. So that now the instruction register is having the current instruction that is going to be executed within the CPU. Understand? So this is the bit. Initially, program counter address is given to memory address register. Then that address given in the memory address register is searched in the main memory. And in the main memory, in the particular location, some instruction is available. That instruction is given to the memory buffer register. Then the memory buffer register transfer the instruction to the instruction register. Memory buffer register transfer the instruction to the instruction register. In this instruction register only, the instruction decoding operation is performed. Okay, instruction. What is instruction decoding? Okay, in the instruction decoding cycle, it will determine what type of operation needs to be performed and what are the operands needed to perform the particular operation. Okay, suppose if we are performing addition operation means the instruction register can determine the type of operation as addition and how many operands needed for performing the operation. That is also determined in the decode stage of instruction execution. Understand? So instruction decode is happening within the instruction register. That is, this instruction register will determine operation needs to be performed, and how many operands means some data. How many data are needed to perform the particular operation? Understand? So after that, after decoding cycle, next the actual execution is performed. Okay, after decoding only, the CPU can decide whether it needs ALU or not. To perform the arithmetic and logical unit, it needs ALU. So in that case, the corresponding operation is performed within the ALU, and the result of this execution is stored in one register called accumulator. So accumulator is a register used to store the result of arithmetic operation performed within the ALU. Understand? Any doubt to this? So in the instruction fetch cycle, initially the instruction available in the main memory is given to the processor. Main memory la mattum irundha execution nadakadu. So this instruction needs to be bring to the CPU. Inge fetch panni CPU la store panna da execution panna mudiyum. So in the instruction fetch cycle, the instructions are fetched from main memory to CPU or processor. Then within the processor, decoding is performed in the instruction register because it needs to decide what type of operation to be performed and how many operands needed for performing the particular operation. So after decoding, actual execution is performed. Actual execution is performed within the ALU. Some operation does not need ALU. Example, loading and storing is not needed with ALU, right? But addition, subtraction, multiplication, division, then logical operations such as AND or NOT. So all these operations need ALU. In that case, the particular operation is performed within the ALU, and the result can be stored in the register called accumulator. Okay. Other than this accumulator, there are some limited number of temporary registers are also available within the CPU to hold the operands. Okay. That is depends upon the architecture of the particular processor. Okay. It can have some limited number of registers. Can you understand up to this? Okay. This is the fetch cycle as well as fetch cycle, decode cycle as well as execution. In the execution cycle, the first thing is here after decoding, instruction register is determine the type of operation. For example, it is addition operation. Add R1, R1, R2. Okay. So in this operation, it will check whether both the operands are already available within the register R1 and register R2. If both are available in the register, means the particular operation is executed within the processor. Okay, suppose if it is not available, it means that will be taken from the memory, that is fetched from the memory, and the particular operation is performed within the ALU unit. Any doubt up to this? Fetch cycle, decode cycle, and execution cycle? Any doubt? Okay. The next operation is one more cycle is used. What about the other cycle and instruction execution? Fetch, decode, execute, and one more cycle. Interrupt. Have studied the interrupt cycle, right? Okay, what is the use of interrupt? Yes, to improve the processor utilization, the interrupt signal is given to the processor, right? So the instruction execution cycle is totally having 4 stages. Just copy the diagram for instruction execution. Keep quiet. Talking diagram. Okay, this is the instruction, execution, operation with 4 cycles, right? Fetch, decode, execute, and interrupt. Check for interrupt. Okay. Listen. The interrupt is a signal. It is given to the processor for improving the processor utilization or CPU utilization. That is, when a user program executes within a CPU, some user program needs some I/O operation. So in that case, the control will be transferred to the I/O program. So while the I/O program is executing, at that time the CPU sits as idle. Okay, the CPU will not execute any operation while the I/O operations are performed. At that time, CPU sits as an idle state. Okay. So, in order to avoid this, in order to improve the CPU utilization, or in order to make the CPU always busy, we can provide interrupt signal. So, when the interrupt signal is enabled, we will call the interrupt service routine. So, here in the execute cycle, if any interrupts are enabled means automatically the control will be transferred to the particular interrupt handler or interrupt service routine. Okay, interrupt service routine or interrupt handler. If there is no interrupt means interrupts are disabled means we don't give any interrupt signal. The CPU is sits as an idle state. Okay, for example, we are going to consider a user program. A user program which consists of the program segments, that is in this program segment 1. After completing this program segment 1, there is some write operation. So write operation means it needs some I/O devices. In that case, the control will be transferred to the I/O program, right? So here there is some I/O program. After executing the sequence of statements in program segment 1, there is some I/O operations are needed in the user program. In that case, control will be transferred to this I/O program. Okay, I/O program. So it will start executing the statements present in program segment 3 up to this end state. Okay, it will start executing all the statement from program segment 3 as well as 4. Okay, at that time, while these I/O operations are performing, at that time the CPU is in idle state. It won't perform any operation. So automatically the performance can be decreased, right? The CPU wastes more time in keeping us idle. While the I/O processes are executing, I/O devices are busy in printing something means at that time the CPU sits as an idle state. So this decreases the performance of CPU. So in order to improve the CPU utilization or in order to improve the performance, interrupt signal, we can introduce one interrupt signal. Interrupt signals are provided, so it will make the CPU always busy in executing. This is the example segment without introducing any interrupt. Here we are not going to introduce any interrupt. First, the program segment 1 is executing. Start from the first line, will execute all the statement in program segment 1. Then it reaches I/O operation. So automatically control is transferred to this I/O program. So it will start executing all the statements in program segment 3 as well as 4. In program segment 3, there is some initial preparation statement for I/O devices are executed. Then here I/O command means the actual I/O operation. When this I/O command is called, it needs some data from the processor to print some content. So at that time, the data can be received from the processor, and finally the I/O processing will be completed after this fourth segment. Okay. So while all these operations are executing in this I/O program, at that time the CPU becomes idle. So this is the normal processing of CPU or normal processing of user program without interrupt. Okay. Then next we are going to see example for executing user program by introducing interrupt. So when we introduce interrupt, when the user program is executing, after completing the program segment 1, it needs write operation. So in that case, the control will be transferred to the I/O program. Executing this preparation statement, here it will give some interrupt signal to the interrupt signals are received in the CPU. receiving the interrupt signal, the CPU start executing the remaining user program, that is the program segment 2 is executed. Will start executing while the IO operation is performing in this IO processor. At the same time, the CPU start executing the remaining codes in the user program. So this you can divide this program segment 2 as 2A and 2B. Okay. Okay, here both CPU and IO processors are executing at the same time. So when this interrupt signal is received, at that time only it will stop the execution of user program. Then it will give the data that are needed by the output devices like printer. Okay, here to perform the IO operation, the IO devices like printer needs data. That data will be given by the CPU only. So in that time it will call the interrupt handler. This is interrupt handler. Okay, in this, when we introduce this interrupt signal, initially the processor start executing the statement from this first statement to up to this. Before this write operation, all the instructions are executed. When write operation is received, at that time control will be transferred to the IO program. Okay, IO program, and it will start executing all the instructions in this IO program. At that time, while the IO program is executing, at that time the CPU is busy in executing the program segment in.